Welcome, everyone. For today's prep, we're going to start to look at Taylor and Maclaurin series. So, let's get to the definitions here. So, given a function f, we're going to look at the Taylor series of f centered at x equals a. So, just like when we were doing power series, we said a was the center value, same thing here. All right, so what is this? What is the Taylor series for this function? Well, it's the sum from n equals 0 to infinity of the nth derivative of our function f evaluated at a divided by n factorial times x minus a raised to the power n. All right, so there's quite a bit going on here. First of all, let's just distinguish. This part is just a constant. So this is our coefficient. When we're talking about power series, this is just our coefficient of the nth term. So this is just a constant. Then the x minus a raised to the power n, that's the actual kind of the variable part of our power series. Now a little bit on the notation here. So because we're going to be dealing with a lot of derivatives when we talk about a Taylor series, we kind of shorten up the derivative notation. So a lot of times we use prime. Prime's pretty good. Prime's a nice shorthand. So the first derivative is f prime, second derivative is f double prime. But once you kind of get past second derivative, 3 primes, 1, 2, 3, kind of gets hard to read. Or the fourth derivative, 1, 2, 3, 4. The primes kind of get a little messy. So we can also indicate derivatives like this with parentheses and then a number. And what this indicates is the nth derivative of our function. So we could say parentheses 4 for the fourth derivative, just a little cleaner. And one thing about the notation also is when we say f of, when n is 0, what does this mean? This just means the 0th derivative. So it's the original function. We haven't done any derivatives yet. So the 0th derivative, just the original function. All right, so we have it written in sigma notation, and this is kind of where we want to go with these. But it does help to just write out the first few terms to see what the Taylor series kind of looks like. So when we plug 0 in, we get our original function evaluated at a, which is what we're seeing here. And then 0 factorial is just 1, and then x minus a raised to the 0 also just 1. So we just get our function value at that center point. Then when n is equal to 1, if we plug in, we end up with our first derivative evaluated at a, so just f prime, divided by 1 factorial. And then our x minus a is just raised to the power 1. And then similar for n equals 2. So there we get our second derivative, so f double prime evaluated at a, divided by 2 factorial, which is what we're seeing here, and then x minus a squared. And we could keep going and going and going, so it just keeps on going. And again, just to remind you, the coefficient terms, when we do these should all be constants. So this ends up just being a number. So f of a, when we evaluate, that should just be a number. F prime of a, when we evaluate, that should just be a number. F double prime at a number. So we'll keep that in mind. Now, Taylor series, this is the general result. But we also talk about Maclaurin series. And the Maclaurin series is really just a special case of Taylor series. So the only thing going on with the Maclaurin is it's just a Taylor series where it's centered at a equals 0. So you can see we're evaluating all of our derivatives at 0. So that's what we end up with, all of our derivatives evaluated at 0. The n factorial part is still the same. And then rather than x minus a, it's going to be x minus 0, and that's just x. So we end up with just these nice powers of x. All right, so Maclaurin series is really just a special case of the Taylor series, where we're kind of focusing in on a equals 0. So let's get a little practice. Let's try writing out the Maclaurin series for the function e to the x. And then once we have that series written out, we'll find the radius of convergence. All right. So how are we going to do this? Well, let's leave some space because we're going to do some work here. But let's write out what the general form is for the Maclaurin series. And this is just the Taylor series centered at a equals 0. So we're going to do the Maclaurin series for this function e to the x. All right, so what's the general sigma notation? It's the sum from n equals 0 to infinity of the nth derivative of our function evaluated at 0 divided by n factorial times all of our power terms, x raised to the power n. All right, so when we're dealing with a series, x raised to the power n, that's perfectly good. The n factorial, also, that's perfectly well understood. The thing we got to work with, though, is this nth derivative. If we want to get this as an explicit series, we got to figure out a formula for this term. So that's the goal. Is we got to try to figure out what's going on, see if we can figure out a pattern for the nth derivative of our function evaluated at the center point. So in this case, evaluated at 0. All right, so to help with that, we're going to start by calculating just a few derivatives to help us get a little list of things, and from that list, hopefully we can figure out the pattern. So that's what we're trying to do here. We're trying to find the pattern. For that nth derivative evaluated at 0. So we're trying to figure out what this is explicitly. All right, so to help us out, let's first calculate the 0th derivative of our function at x. Then we'll calculate the first derivative of our function at x. And let's do, normally it's a good idea to write out the first, 4 or 5 terms just to kind of get a good sample of what's going on. So let's do up to our 4th derivative evaluated at x. So let's calculate all these. So what's our 0th derivative? Well, that's just the original function. So not too bad, e to the x. And we're starting off kind of easy here. So, all right, so now let's differentiate this, e to the x. Well, derivative of e to the x is just e to the x. Okay. So we've got our first derivative. Now to get the second derivative, we do it again. And derivative of e to the x is nice, just e to the x. We'll get more complicated, don't worry. And then we want our third derivative, so we take our second derivative, differentiate that. Also, for this special one, e to the x. And then same thing for our fourth derivative. It's e to the x. So once we actually calculate all these different derivatives, then we'll plug in our number. So we want to plug in this case, a equals 0. We want to plug in that center point. So let's see what we get. We'll take our 0th derivative, plug 0 in. Then we'll take our first derivative, plug 0 in. Our second derivative, we'll plug 0 in. Our third derivative, we'll plug 0 in. And our fourth derivative, we'll plug 0 in. So what do we get? Well, in each of these, we get e raised to the 0. So I'm going back to the function and just swapping out the x with a 0 now, or whatever our center point is. So for each of these, it's just e to the 0. I'm just going back, taking the function that we found, swapping out the x with our center point. And that's not a 6. That's a 0. And then same thing for our fourth derivative. And if we simplify these, e to the 0 is just 1. All right, so trust me, when we get to other functions, this is going to help to have a list. So the goal is we want to find the pattern so that we could guess what the nth derivative evaluated at 0 is. Well, the first one here is 1. The second one here is 1. The third one is 1. Fourth one is 1. Fifth one is 1. You can probably guess. So in general, if we kind of look at this list and guess, the nth derivative of our function here evaluated at 0 is just going to be 1. So that's not always the case. In fact, for most functions, that's not going to be the case. All right. So now that we've figured out what the nth derivative evaluated at our center point is, we found a formula for that nth derivative. Now we can plug that in. So we're going to replace this nth derivative evaluated at 0 with what we found. And a lot of times this formula should have n's in it. So this formula might have other constants and things, but it most likely will have some n terms as well. Now for here, this is an easy one, so it's just a constant sequence. All right, so if we fill that in, we end up with the series n equals 0 to infinity, 1 over n factorial times x raised to the n. And a lot of times we will write this as, we'll just combine it into a single fraction. So we'll have the sum of x raised to the n over n factorial like that. And just to kind of see what this thing looks like, let's write out the first few terms. So the first term when n is 0 is just 1. The second term is just x. The third term is x squared over 2 factorial. And let's go one more. X cubed over 3 factorial, and so on. So this is the Maclaurin series for e to the x. All right. Now what about the radius of convergence? We want to find the radius of convergence for this function, or this power series. Well, if we remember, how do we get the radius of convergence for just a arbitrary power series like this? So this power series here is not related to a geometric series. So what we did here, this is not a geometric series. So when it's not a geometric, the way we get the radius of convergence is we have to use our ratio test, usually our ratio test. If this was a geometric series, then there's that little shortcut that we've been seeing for those 1 over 1 minus x functions. There's that little shortcut. But this is not a geometric series, so we didn't use 1 over 1 minus x here at all. We're not relating this back to a geometric, so we just got to calculate the radius of convergence the old-fashioned way, ratio test. So, remember, first step for doing the radius of convergence is we calculate that gadget an plus 1 over an. And when we do this, let's do the an plus 1 fraction first, and then next door we'll do the reciprocal of an. So our an plus 1 fraction, we'll go back to here, and that'll be x raised to the n plus 1 over n plus 1 factorial. And then next door to that, we'll have the reciprocal of an. So it'll be this term, but just flipped. So n factorial on the top, and then x raised to the n on the bottom. Again, rearrange the terms. So let's get all the x's grouped together and then all the factorials grouped together. And we've probably done this one at some point. Feels kind of familiar. But let's simplify the x's here. So we don't know what x is, so we still need our absolute value around that part of our fraction. And then the factorials here, well, we've seen this before. The n plus 1 factorial is the same thing as n plus 1 times n factorial. So in this case, the n factorial will cancel off that n factorial, and we're going to be left with just 1 over n plus 1. All right, so that's what we get when we simplify down that ratio test gadget. Then, once we've done that, then we do the limit. So we do our ratio test limit. So limit of absolute value an plus 1 over an, with n going to infinity. Let's use the simplified version. So absolute value of x times 1 over n plus 1, with n going to infinity. And again, let's just remember, we're doing the limit as n gets larger and larger. So this absolute value x, this is just a constant. So this thing is not changing for any particular x value. This is the thing that's changing. And as n gets bigger and bigger, this is a c over infinity form. So this whole limit goes to 0. So we had a c over infinity form here. All right. So we figured out our limit. And what this says is no matter what x value you plug into this, your limit's always going to be 0. So what we found is that since the limit L from our ratio test is 0, is always 0, and that's always going to be less than 1, this is true for any x value. So even if x was like 1,000,000, well, eventually, this fraction 1 over n plus 1 is still going to go to 0. So even if this was 1,000,000, big number, this term is still going to get really, really small. N's going to get bigger than 1,000,000, so this fraction is going to get really close to 0. So this limit always goes to 0 here. So because of that, we're able to conclude, since our limit L is always going to be less than 1 for all x values, that means our interval of convergence is the entire x-axis. It just includes all x values. And from that, we can find our radius of convergence, which, well, it's half the width. It's an infinite width here, so half of infinity is still infinity. So our radius of convergence, we say, is infinite. All right. So in this example, we've found the Maclaurin series for our function e to the x. And we've shown that the interval of convergence and the radius of convergence for this power series include all x values. All right, so we'll get some more practice with these examples, and in class we're gonna look at the next example, and we're gonna make one change, not just e to the x. I'm gonna spice it up a little bit. Let's do e to the 2x. So if you want to try out, think about what the derivative of this function is going to be. We got to use our chain rule here. So think about what this derivative is going to be, and then we'll be starting with this one in class. So we'll see you then. Bye-bye.